So up until this point, we've talked about functions of just one variable and finding their minimum or maximum. But remember when we were talking about residual sum of squares, we had two variables, two parameters of our model, w0 and w1, and we wanted to minimize over both. So let's talk about how we're going to move to functions defined over multiple variables. So moving to multiple dimensions here, where when we have these functions in higher dimensions, we don't talk about derivatives anymore, we talk about gradients in their place. And what a gradient is, so let me write this. This is the notation for the gradient of a function where this w is really a vector of different w's. So let's say w0, w1, all the way up to some w, I didn't leave enough room there, sorry, to some wp. And what the gradient is, it's pretty straightforward actually, the definition. It's going to be a vector where we're going to look at what are called the partial derivatives of g. So we're going to look at the partial with respect to w0, the partial of g with respect to w1, all the way up to the partial of g with respect to some wp. And let's describe what one of these looks like. So for example here, this partial derivative, it's exactly like a derivative where we're taking the derivative with respect to, in this case, w1. But what are we going to do with all the other w's, w0, w2, w3, all the way up to wp? Well, we're just going to treat them like constants. Okay, it's as if they were just numbers like 5, 7, and 10 when we talked about taking derivatives in one dimension. Okay, so the partial derivative is like a derivative with respect to w1 in this case, treating all other variables as constants. Okay, so just to be clear, this gradient is, in this case, if we assume that there's some variables w0 all the way up to wp, there's a reason I'm using this notation. We'll see it later in this course, but this represents a p plus 1, because we're indexing and starting at 0. This is a p plus 1 dimensional vector. Okay, so let's work through a little example here where I defined a function g of w to just be 5 w0 plus 10 w0 w1 plus 2 w1 squared. And let's compute the gradient of w. And in this case, they're just two variables, so I have to take the partial of g with respect to w0. So I'm going to take the derivative of this thing here, only interested in w0. So this term, I get a 5. The next term, well, I'm treating w1 like a constant. So just like I would take the derivative and get the constant as the result, that's what I'll get. So there's a 10 and there's a w1. And then I take the derivative of this term. It has nothing to do with w0. It's just like a constant. So the result is going to be 0. Now I take the partial with respect to w1. And this first term is just a constant with respect to w1, so it doesn't appear. This next term, well, I end up with these two terms as the coefficient for w1. And then I get to this last term, and again, using the same derivative properties we talked about before, when I have something to a power, I'm going to bring that power down. So I'm going to get 4 w1 raised to the 1 power. Okay, so my gradient of g is going to be 5 plus 10 w1, 10 w0 plus 4 w1. So what does this mean? Well, if I want to look at, let me switch to the red color so you can see it on this plot. if I want to look at the gradient at any point on this surface, well, I'm just going to plug in whatever the W1 and W0 values are at this point. So there's some W0, W1 value, and I'm going to compute the gradient. And it'll be some vector. It's just some number in the first component, some number in the second component, and that forms some vector.